Every year, an estimated 19 to 23 million metric tons of plastic waste leak into rivers, lakes, and seas. That is roughly 36 to 44 metric tons every minute. Some of it sinks near the coast. Some becomes trapped in wetlands or buried in sediment. The rest can be carried through rivers, pushed along coastlines, and transported thousands of kilometers by ocean currents. The largest known accumulation lies between California and Hawaii. The Great Pacific Garbage Patch covers an estimated 1.6 million square kilometers and contains around 100,000 metric tons of floating plastic. Yet this is not a solid island of garbage. It is an estimated 1.8 trillion separate pieces, spread across an enormous and constantly moving area of ocean. Cleaning it up requires far more than sending out a ship with a large net. How do you collect plastic when it is spread across thousands of kilometers of ocean? How do these systems avoid collecting marine animals along with the waste? And once the plastic reaches land, can any of it actually be recycled? To answer those questions, we first need to understand what ocean plastic actually looks like once it enters the water. The Great Pacific Garbage Patch does not look like its name suggests. There is no visible island of bottles, bags, and fishing nets floating in the middle of the Pacific. A ship can travel through part of the accumulation zone without seeing anything that resembles a landfill. Most of the plastic is spread thinly across the surface. Its concentration gradually increases toward the center of the patch, but even there, the material is separated by large areas of open water. The distribution also keeps changing. Wind pushes objects that sit partly above the surface. Waves force some pieces underwater and bring others back up. Ocean currents move the debris in different directions and continually reshape the densest areas. A cleanup vessel is not traveling toward a fixed pile of garbage. It is searching for temporary concentrations that may have moved before the ship arrives. The plastic itself comes in very different forms. Some pieces are almost microscopic. Others are bottle caps, containers, crates, ropes, or fishing nets several meters long. Although microplastics account for about 94% of the estimated number of pieces in the patch, they represent only around 8% of its total plastic mass. More than 3/4 of the estimated mass comes from objects larger than 5 centimeters. The 2018 survey also estimated that fishing nets accounted for at least 46% of the total mass. That difference determines what large cleanup systems are designed to collect. Trying to filter every microscopic particle would mean passing enormous volumes of seawater through an extremely fine screen. That same water contains plankton, fish eggs, and other small organisms. A machine capable of removing nearly every plastic particle would also interfere with much of the life moving through the upper ocean. Large systems therefore concentrate on the heavier share of the problem: nets, ropes, rigid objects, and fragments that are still floating and large enough to capture. Even these objects do not remain in one place forever. A buoyant fishing net may stay near the surface for years. A bottle can fill with water and sink. Plastic can become covered with algae, shells, and other organisms, making it heavier. If some of that growth later detaches, the object may rise again. Once plastic sinks far below the surface or breaks into tiny fragments, recovery becomes much more difficult. The best opportunity often comes earlier, while the waste is still moving through a river and has not yet spread across the ocean. Plastic discarded on land can enter storm drains during heavy rain. Waste from open dumps may wash into nearby streams. Smaller waterways carry it into larger rivers, which transport it toward the coast. At this stage, thousands of separate objects may still be moving through a relatively narrow channel. A 2021 study estimated that more than 1,000 rivers account for approximately 80% of annual riverborne plastic emissions into the ocean. Many are not enormous rivers. Small and medium-sized urban rivers can become major sources when they pass through densely populated areas, receive poorly managed waste, and have a short route to the sea. The river has already concentrated the material and supplied the force moving it downstream. A collection system can use both. One of the best-known designs is the interceptor originally developed by the Ocean Cleanup. A long floating barrier is installed at an angle to the current. It does not close the entire river. Boats can continue to pass through the open section, while floating debris is pushed along the barrier toward an entrance between two hulls. The current carries the debris onto a permeable conveyor belt. Water passes through the belt, while bottles, packaging, branches, and other objects are lifted from the river. At the top, the waste drops onto an automated shuttle. The shuttle moves from side to side and distributes the material between 6 dumpsters mounted on a separate barge. Sensors measure how full each dumpster has become and direct new loads toward the available space. Together, the containers can store up to 50 cubic meters of waste. When the barge approaches capacity, the system sends a message to local operators. They tow the barge to shore, empty the dumpsters, and return it to the machine. The conveyor, shuttle, lights, sensors, and communication equipment are powered by solar panels. The river supplies the movement that brings waste to the system, while electricity is mainly needed to lift and distribute it. Not every river can use the same design. In Baltimore, Mr. Trash Wheel combines floating booms, a conveyor, and a large water wheel. The booms guide debris toward the machine, and the river current turns the wheel that drives the conveyor. When the current is too weak, solar-powered pumps move additional water over the wheel. The waste is lifted from the harbor and dropped into a dumpster on a separate barge. The machine runs slowly and is normally activated when debris is present, particularly during and after rainstorms. Other waterways cannot place a physical barrier across the surface because too many boats pass through them. The Great Bubble Barrier uses a perforated tube installed diagonally across the riverbed. A compressor forces air through the tube, creating a continuous curtain of bubbles. The rising bubbles generate an upward current that brings some submerged plastic toward the surface. Because the tube crosses the waterway at an angle, the natural river flow gradually carries the debris sideways into a collection unit near the bank. Boats can pass above the tube, and fish are not physically blocked by a boom stretching across the channel. These designs all use the same basic advantage. The waste is already moving toward them. A river machine may operate automatically for long periods, but it still needs maintenance crews, trucks, and a waste facility on land. The equipment can remove material from the water only when the system behind it has somewhere to take the catch. Once plastic reaches the open ocean, there is no fixed riverbank and no single current delivering the waste to one point. The collection system has to move through the water and create a temporary bottleneck of its own. The Great Pacific Garbage Patch lies far from the nearest port. Reaching the area can take several days, and a cleanup mission may remain offshore for weeks. System 03, first deployed in the patch in 2023, uses 2 slow-moving vessels towing the ends of a floating barrier approximately 2.2 kilometers long. A flexible screen extends 4 meters below the surface. It is deep enough to retain much of the floating plastic without attempting to sweep the deeper water column. The 2 vessels hold the barrier in a wide U-shape and maintain a small speed difference between the system and the plastic drifting around it. Plastic enters through the wide opening between the vessels. The long wings gradually guide it toward a narrower retention zone at the rear. Water continues to flow through the screen while larger debris remains inside. Moving slowly reduces the forces on the barrier, lowers fuel use, and gives animals more time to move away from the system. When the retention zone contains enough plastic, the ships bring the 2 sides of the system closer together. The entrance is closed, and the rear section is pulled alongside one of the vessels. A crane lifts the retention zone onto the deck and empties the catch, Crew members separate large nets and objects, pack the material into containers, and return the collection section to the water. The same currents that concentrate plastic also carry marine life. Fish, turtles, jellyfish, and organisms living near the surface may enter the system with the debris. Avoiding them requires more than simply leaving gaps in the screen. Environmental observers monitor the surrounding water and document interactions with marine animals. Cameras are positioned around the collection system, and operating routes can be adjusted to avoid conditions associated with sensitive species. System 03 also includes the Marine Animal Safety Hatch. If an animal is detected inside the retention zone, the hatch can block further entry and open a route through which the animal can leave without releasing the entire plastic hatch. These measures reduce the risk, but the collection area still has to be monitored continuously. A system operating in an ecosystem cannot assume that everything entering the barrier is garbage. Finding plastic creates a separate challenge. The patch is enormous, but its debris is not distributed evenly. 2 vessels can tow a 2-kilometer barrier through water containing very little plastic. Increasing the size of the system does not improve the catch if it is operating in the wrong place. Earlier missions relied on ocean current models, observations from ships, and floating GPS markers to estimate where the debris was likely to accumulate. The next stage adds automated cameras, artificial intelligence, and aerial drones. The smart steering strategy combines wind, wave, and current data with models of how the patch moves. These models can produce a general forecast of where dense areas may travel during the following days. Closer to the ship, drones can fly ahead of the vessels and photograph the surface. Image detection systems identify possible plastic objects and map areas with higher concentrations. The route can then be changed before the ships spend hours towing through relatively empty water. A 6-week Pacific data expedition scheduled for July and August 2026 was designed to test this approach in the garbage patch. Simulations cited by the Ocean Cleanup suggest that drone-assisted navigation could more than double the impact of a collection system by directing it toward denser concentrations rather than increasing the number of vessels. Open ocean cleanup is therefore not only a question of building a long barrier. It is also a problem of forecasting where the waste will be, navigating toward it, and keeping the collection system inside the densest part of a moving target. Once the plastic has been found, concentrated, and lifted onto a ship, the machines have completed only the first half of the job. Plastic taken from the ocean does not arrive as clean recycling material. It may have spent years exposed to sunlight, salt water, and constant movement. Nets can be covered with biological growth. Containers may have lost their labels. Ropes can contain several polymers twisted together, along with metal fittings and other materials. This creates 3 main obstacles. The first is contamination. Salt, sand, oil, mud, and organic matter have to be removed before the plastic can enter normal processing equipment. The second is degradation. Ultraviolet radiation and mechanical work can damage the polymer structure, reducing the strength and consistency of the recycled material. The third is separation. Polyethylene, polypropylene, nylon, and other plastics have different melting temperatures and physical properties. Combining incompatible polymers can produce weak or unreliable material. The catch is first divided into broad groups. Rigid plastic is separated from fibrous materials such as ropes and fishing nets. Metal, wood, and other unwanted objects are removed. The plastic is then sorted more precisely by polymer type. It may be shredded into smaller pieces so that salt and contamination can be washed from a greater surface area. After washing and drying, suitable material is melted and pushed through an extruder to form granules. Those granules are tested for contamination, strength, and consistency before they can be used in a new product. Selected ocean plastic has completed this process successfully. plastic recovered from the Great Pacific Garbage Patch was used in a limited edition trunk liner developed by Kia. The finished product contains 40% recycled ocean plastic, combined with other materials needed to produce the required durability and performance. That does not mean 40% of every ocean catch becomes a car part, or that all material taken from the water can be recycled. Clean pieces made from an identifiable polymer have the best chance. Mixed, heavily degraded or contaminated objects may not meet the requirements for mechanical recycling. Some material has to be incinerated, co-processed, or sent to a controlled landfill. The outcome depends on the infrastructure available near each project. In Guatemala, recoverable PET collected from the Rio Motagua system has been sent to a processing plant in Honduras, where it can be used in products such as pillows, mops, and brushes. Organic material can be composted, while usable wood may be separated for other purposes. In locations without nearby buyers or recycling facilities, far less of the catch can be recovered. The ocean cleanup reports that only a small portion of the waste collected from some rivers is currently recycled or reused. The remainder is handled through locally available disposal routes. The answer to whether ocean plastic can be recycled is therefore yes, but only for selected parts of the catch. Collection does not automatically transform waste into a valuable raw material. Recycling depends on what the object was originally made from, how long it remained in the environment, how badly it has degraded, and whether suitable processing equipment exists nearby. Each collection system operates within a narrow physical range. River interceptors collect waste that passes through their section of the river, remains near the surface, and reaches the barrier. Harbor machines work in protected water, but cannot cross thousands of kilometers of ocean. Offshore barriers can target large floating objects in accumulation zones. They cannot recover plastic buried in sediment, stranded across remote coastlines, or resting on the seabed. Once the material becomes microscopic or sinks beyond the operating depth of the system, large mechanical collection is no longer practical. The cost also rises sharply as the plastic moves farther from land. In 2024, the Ocean Cleanup estimated that eliminating the Great Pacific Garbage Patch at the performance level demonstrated at that time would take approximately 10 years and cost around $7.5 billion. Its modeling suggested that better hotspot detection and more efficient operations might reduce this to 5 years and approximately $4 billion. These are projections published by the organization operating the system, rather than the cost of a completed cleanup, but they show the financial scale of working in the middle of the Pacific. Much of the expense comes from the vessels. A longer barrier is useful because it allows each pair of ships to sweep a wider area. More systems would require more crews, more fuel, more maintenance, and more support ships. The equipment floating between the vessels is only one part of the operating cost. And even after the plastic is brought ashore, much of it has little commercial value. Sunlight, salt water, and years of physical damage reduce its quality, while sorting and cleaning add further costs. This means ocean cleanup cannot pay for itself through recycled plastic alone. It depends on funding, partnerships, and people willing to keep the ships operating even when the material they recover is worth far less than the cost of collecting it. These systems cannot remove every piece of plastic from the ocean, but every net, rope, and container recovered is one less object left to break apart, drift for decades, or continue harming marine life. Whatever their limitations, let us pay tribute to the organization's engineers and crews dedicated to cleaning our oceans. Thanks for watching. If this video changed how you see ocean cleanup, please like the video and subscribe to the channel for more stories about the hidden systems behind the world around us. We'll see you in the next one.